Some machines don't just move, they dominate. And at the core of these machines, gears. Not the kind in your wristwatch or car transmission. We're talking about industrial gears so massive they have to be transported on flat trucks. Gears taller than a person. Gears that weigh more than a tank. And yet, they spin with incredible precision, day in and day out, in some of the harshest environments on the planet. These mechanical beasts live inside cement kilns, wind turbines, mining crushers, steel mills, and giant ships. They handle brutal torque, unforgiving friction, and non-stop operation without flinching. What makes that possible isn't just the size, it's the way they're made. A single gear tooth, slightly out of spec, can bring an entire factory line to a halt. These gears are crafted in stages that blend old-school metalworking skills with cutting-edge technology. From selecting the perfect steel alloy to heat treating, precision machining, tooth grinding, and microscopic inspections, every step is calculated. It starts with a steel blank that looks like a giant donut. Then comes the rough shaping. After that, the real magic begins. Massive CNC machines shape each tooth with surgical accuracy. Some factories even grind gear teeth to a mirror finish. Why? Because even the tiniest surface flaw can turn into a catastrophic failure under extreme load. The end result? A gear that might look like a simple circle of metal, but in reality, it's a masterpiece of engineering. Tough enough to move mountains, precise enough to pass inspection down to the micron. So how do they do it? What's it really take to build something this powerful, this perfect? Let's go inside the world of giant industrial gears. The birth of a giant, choosing the right steel. Every giant gear starts with one big decision. What kind of steel will it be made from? It sounds simple, but this choice can make or break everything. Not all steel is the same. Some are soft, some are hard, some can handle extreme pressure, while others might crack under stress. The gears used in heavy machines, like mining trucks, wind turbines, or ships, need a special kind of steel. It has to be super strong, but not too brittle. It must survive heavy loads, high speeds, and crazy heat, day after day, year after year. So, how do they choose the right one? Metallurgists, basically metal scientists, create the perfect recipe. They mix iron with elements like nickel, chromium, and molybdenum. These ingredients make the steel stronger, tougher, and better at handling stress. It's not just about making it strong. It has to be strong in the right way. Strong but not too hard. Tough but still machinable. If the recipe is wrong, the gear might crack later. And in the real world, a failed gear can shut down an entire factory or even cause a serious accident. Once the perfect steel is chosen, it's melted in massive furnaces, heated to over 1,500 degrees Celsius, and shaped into bars or blanks. These will later become the giant gears we see in heavy industry. This moment, the choice of steel, is the true beginning, because no matter how perfect the process is later, it all depends on starting with the right metal. Forging the beast. How raw metal becomes a gear blank. Once the right steel is made, it's time to shape it into something real. But not the final gear just yet. First, it becomes a gear blank, a thick, heavy disc that's ready to be carved. And take that blank, you need forging, one of the oldest and toughest metal shaping methods in the world. The steel is first heated until it glows orange or even white. That's over 1,000 degrees Celsius. At this temperature, it's still solid, but soft enough to shape. Then it's placed under massive machines, forging presses or hammers that smash it into shape with incredible force. We're talking about thousands of tons of pressure. Every hit makes the metal stronger by squeezing out tiny defects and aligning the grain inside. This makes forged steel much tougher than cast or rolled metal. Depending on the size of the gear, the blank could be as small as a car tire or as big as a hot tub. Some even weigh over 20,000 kilos. There are different types of forging too. Open die forging is used for really large gears, where the metal is shaped bit by bit. Closed die forging is more precise, used for medium-sized parts with more detailed shapes. After forging, the blank is cooled slowly to avoid cracks. It's now rough, solid, and super strong, ready for the next step. It might not look like a gear yet, but this is where the real transformation begins. Rough machining, shaping the monster. Now that we have a solid steel blank, it's time to start shaping it into something that looks like a gear. This step is called rough machining, and it's where the monster starts to take form. But you can't just throw a chunk of steel into any machine. These gear blanks are often too big to lift by hand, so they're moved using cranes and forklifts. The machines that cut them, also huge. Some are the size of a small room. They use CNC technology, which means computer-controlled cutting tools that can follow exact shapes. In this stage, we're not looking for final perfection. The goal is to remove all the extra material and give the gear its basic shape. This includes flattening the surfaces, cutting the center hole, and forming the outside circle. Giant cutting tools spin at high speeds, shaving off thick chunks of steel. You'll see sparks flying, coolant spraying, and metal chips pouring off like water. It's loud, intense, and impressive to watch. Even though it's called rough, this step still has to be super accurate. If the shape is even a little off, the gear won't fit or turn right later. That's why machinists measure everything carefully, even at this early stage. Once the blank is shaped, it's starting to look like a real gear, but without any teeth yet. Right now, the monster has its body. Next, it gets its bite. Precision gear cutting, carving teeth with micron accuracy. Now comes the part that really makes a gear, the teeth. At this stage, the steel blank looks like a giant metal donut. But without teeth, it's useless. Those teeth are what transfer power, spin heavy machines, and keep everything moving in perfect sync. And cutting them? That's where the real magic happens. This step is called gear cutting, and it needs to be done with extreme accuracy. We're talking measurements down to microns. That's smaller than a human hair. If one tooth is even slightly off, it can cause vibration, wear, or total failure. There are a few ways to cut gear teeth. One of the most common is hobbing. A spinning tool called hob slowly cuts each tooth as the gear rotates. It's kind of like peeling an apple in perfect spirals, but it's steel. For more complex or larger gears, other methods like shaping or broaching might be used. These tools don't just cut, they carve, shave, and sculpt the steel with incredible precision. And the machines doing this work, they cost hundreds of thousands of dollars and need expert operators. Every cut is checked, double-checked, and then checked again. By the time this step is done, the gear has its final shape, strong, perfect, and sharp. It's not just a hunk of metal anymore. It's a fully formed gear ready to handle massive loads, but it still needs one more thing to survive the real world: heat. Heat treatment, turning steel into supersteel. Now that the gear has its final shape, it looks strong. But looks can be deceiving. At this stage, it's still not ready for real work. If it goes into a machine right now, the teeth could wear out or even break under pressure. This is where the real transformation happens: heat treatment. It's like giving the gear superpowers. The gear is heated in giant ovens, called furnaces, to temperatures as high as 900 to 1000 degrees Celsius. That's hot enough to glow bright orange. At this heat, the steel's internal structure changes. It becomes harder, tougher, and more resistant to wear. But here's the trick. You can't just heat it up and walk away. After the gear is heated, it must be cooled down in a very controlled way. Sometimes it's tipped in oil, water, or even gas, depending on the type of steel. This sudden cooling is called quenching. Get the timing wrong, the gear could crack. Cool it too slowly, it stays soft. It's a science and art, and only experts can get it right. Sometimes the gear is also tempered afterward, heated again, but at a lower temperature to make it less brittle. This step gives it a perfect balance, hard on the outside, tough on the inside. After heat treatment, the gear is no longer just a piece of shaped metal. It's now supersteel, ready to handle extreme pressure, high speed, and years of hard work. Grinding and finishing, mirror smooth and dead-on accurate. After the gear undergoes heat treatment, it's strong, but it's still a bit rough. The next crucial step is grinding and finishing, where the gear gets polished into perfection. Think about it this way. The gear is like a sculptor's work in progress, strong but with jagged edges and rough surfaces. Grinding is like taking a block of stone and smoothing it out until it's ready to shine. In the case of industrial gears, this means using massive high-speed grinding machines with abrasive wheels that spin at incredible speeds to smooth out the rough spots. It's an intense process where every millimeter counts. The purpose of grinding isn't just to make the gear look nice. It's all about precision. Even the smallest imperfections can affect how well the gear meshes with other gears. The teeth must be ground perfectly smooth, so they fit together flawlessly when the machine starts working at full speed. Any bump or dip could cause uneven wear, vibrations, or even a breakdown. That's why grinding is so critical. It's where the gear takes its final shape. Grinding also ensures that the gear is micron accurate, down to the thickness of a human hair. The machines are so precise that even the tiniest flaw is smoothed out. After grinding, the gear is checked again to ensure it meets exact specifications. Once the surface is smooth, it's time for the finishing touches. The gear gets polished to a mirror-like finish, reducing friction and making it more durable. A smoother surface means less heat, less wear, and less energy wasted. The result? A gear that can handle extreme pressure without breaking down, running efficiently for years. Inspection. Hunting for microscopic flaws. Once the gear is ground smooth and polished to perfection, it's not ready to go out the door just yet. Before it can be put into a machine or sent to the customer, it has to pass one of the most important steps, inspection. This is where everything is checked with microscopic precision. We're talking about catching flaws you could never see with the naked eye, cracks, weaknesses, or imperfections that could make the gear fail under pressure. A small defect could lead to major problems down the road. And when gears are used in massive machines, even the tiniest flaw could be catastrophic. To find these invisible issues, technicians use advanced tools and techniques. One of the most common is ultrasonic testing, where sound waves are used to detect cracks or voids inside the gear. Another method is magnetic particle testing, where the gear is coated with a special liquid that highlights cracks when exposed to a magnetic field. There's also dye penetrant testing, where a special dye is applied to the gear's surface. After it's cleaned, the dye will seep into any cracks, making them easy to see. These tests help ensure the gear is free from any defects that could lead to failure. This step doesn't just check for cracks. Measurements are taken again, especially on the teeth. The teeth must fit perfectly with other gears, so they're measured down to microns, making sure every tooth is even and precise. Once it passes all tests and checks, the gear is officially ready for use. It's strong, flawless, and prepared to handle the toughest jobs. Transporting the Titans. How these beasts are moved. These giant gears aren't small. They're massive, often weighing tons, and moving them from the factory to their final destination is a challenge in itself. Transporting these Titans requires careful planning, precision, and equipment designed for the job. The first thing to understand is that these gears can be as large as a small room or even bigger. Transporting them isn't like moving a regular part. It requires special trucks, trailers, and sometimes even heavy-duty cranes. Once the gear is ready, it's loaded onto a flat truck or heavy-duty trailer. But even the most powerful trucks can't just drive anywhere with these beasts. The roads need to be carefully surveyed to make sure they can handle the weight. And sometimes, special permit approvals are required for such oversized loads. This means getting a clear route without low bridges or tight turns. For the largest gears, like those used in mining equipment or wind turbines, they may need to be transported by rail or ship. When this happens, huge cranes are used to lift the gear onto the transport vehicle. Sometimes, gears even need to be shipped across the ocean to another continent, an operation that involves precision logistics and specialized shipping containers. The process doesn't stop once the gear reaches its destination. At the site, the gear is often moved into place using giant cranes or hydraulic jacks, carefully lowering it into position in the machine or factory. Every step, from loading to unloading, is carefully planned and executed. One wrong move and a multi-ton gear could be damaged. But when it's done right, the gear is safely in place, ready to power some of the world's largest machines. Installation and testing. Making sure the gear works. After all the forging, grinding, and moving, the gear has finally reached its destination. But the journey isn't over yet. It still needs to be installed and tested, because a perfect gear on the floor is useless if it doesn't work properly once it's in place. Installing a giant gear isn't as simple as sliding it into a machine. These gears are huge, heavy, and incredibly precise, so even the smallest misalignment can cause big problems. Teams of engineers and technicians work together to position the gear using hydraulic lifts, cranes, and laser alignment tools. The gear is carefully fitted into its system, usually alongside other gears, shafts, or motors. Every connection has to be tight, every angle just right. Once it's in position, the real test begins. The gear is run at low speed first, to check for any unusual movement, sounds, or heat. If anything seems off, the whole system is paused and adjustments are made. Then, it's slowly pushed to full speed under controlled conditions. Sensors are often used to track things like vibration, heat, and torque. If the gear passes all tests, it's considered ready for regular operation. But this step is more than just routine, it's crucial. A missed flaw during testing could lead to costly breakdowns later on. In some cases, test runs can go on for hours or even days, especially in high-stakes industries like aerospace, power generation, or heavy mining. Once everything checks out, the gear is finally signed off and ready to work. After all the intense steps before this, it's satisfying to see the giant gear doing exactly what it was made for, running strong, smooth, and silent. Real-world Titans, where these gears actually works. So, after all the steel making, forging, cutting, grinding, testing, and installing, where do these monster gears actually go? The answer: everywhere power meets pressure. These gears are the hidden giants behind some of the toughest jobs on Earth. Start with mining. Giant excavators, drag lines, and crushers all rely on massive gears to move mountains, literally. These machines chew through rock day and night, and they need gears that won't fail under extreme stress. Then there's wind energy. Inside every wind turbine, there's a powerful gearbox with massive gears that convert the slow spin of the blades into high-speed energy. These gears must run for years in extreme heat, freezing cold, and howling winds without breaking down. Steel mills and cement plants also rely on giant gears. Their kilns and rolling mills use gears taller than people to spin, press, and grind raw materials into usable products. One small failure here could stop an entire factory. Don't forget ships and submarines. The propeller shafts of huge cargo ships are turned by giant gears deep below deck. These gears must work non-stop across oceans without missing a beat. And yes, even space and defense systems use custom-made, ultra-precise gears in their ground-based launch platforms and satellite systems. These gears don't just work, they carry the load of industries, often running for decades. You'll probably never see them, but they're turning silently in the background of nearly everything that keeps the modern world going. They may be hidden, they may be quiet, but they are the true muscle behind machines, the giants that never stop turning. Behind every towering crane, roaring turbine, or earth-crushing excavator, there's a gear doing the hard work, silently, reliably, relentlessly. What seems like just a spinning chunk of metal is actually the product of extreme engineering, precise craftsmanship, and unforgiving standards. It's easy to overlook what we can't see, but these massive gears are the hidden giants that keep the world running. Without them, industries stop. Now that you've seen what it takes to create one, every cut, every grind, every test, you know there's nothing simple about it. It's a reminder that even the toughest machines rely on human brilliance and attention to detail. So next time you see a wind turbine on the horizon, or hear the distant rumble of a freight train, just remember, somewhere inside a gear is turning, and a whole world is moving with it. Thanks for watching. Hopefully, this gave you a new appreciation for the incredible work that goes into building the gears that power the world's biggest machines. They may not get the spotlight, but without them, nothing moves, literally. If you enjoyed this breakdown, go ahead and hit that like button. It tells the algorithm this is worth sharing, and it lets us know you want more content like this. Got thoughts, questions, or suggestions for future topics? Drop them in the comments. We're always listening, and your feedback helps shape what comes next. And if you're into the world of heavy industry, mechanical engineering, or just love seeing how complex things are made, make sure to subscribe. We've got more videos coming that explore the machines, tools, and tech behind the scenes of modern life. Turn on notifications so you don't miss a thing. Whether it's gears, turbines, engines, or entire factories, we're here to show you how it all works, piece by piece.